Hello everyone, and welcome to this webinar on modelling rail electrical systems in MATLAB and Simulink. My name is Dudgeon, and I am an industry manager at MathWorks. In this webinar today, the overall theme is going to be model fidelity. What level of detail do we need in a particular model? Why we're actually doing a simulation in the first place? And really what tools and options are available to us to create models of appropriate fidelity for a given engineering task. We're going to consider two systems in this webinar. The first is a hybrid electric system for a railcar, or a bi-mode railcar, that contains a rechargeable energy storage system. And we're going to be looking at a simulation of this system to assess the technology and also assess operational options for energy recovery. For example, during a braking sequence where we have regenerated electrical energy. We'll also look at an electrified track example. So we'll look at how we model a moving electric load, and we'll be doing this to assess the impact of rail electrification on grid response. So when we think about these two examples, both of them can inherently be very complex. For the hybrid electric system, if we are modeling modular multi-level converters, which is what we're going to be looking at here, then we have to think about how we best approach that modeling task. Because if we're looking at 48 cell, 96 cell type architectures or even higher, we need to think about a way that is appropriate for modeling those systems, because we really don't want to put together multi-level converters by hand, especially those systems that have hundreds of individual components. For the grid-connected moving loads, we emulate the moving loads by using lumped parameter segments. And both of those considerations point towards building the models programmatically, and we'll see this as we go through this webinar. We also want to look at how we can model and simulate different operational scenarios. So I'll briefly touch upon how we can set up scenarios within MATLAB and then have them automatically execute a simulation or a number of simulations in Simulink. So when we're faced with this task of modeling a complex system, we really do want to look at ways in which we can make this more time efficient for us. But time efficiency is not the only thing here. We want to be able to take advantage of techniques that are available to us that help the entire process. So not just from the time perspective, but also from the quality of the model. So the more complex a model is, the greater effort is needed to verify the correctness of that architecture. And so we can build these systems programmatically. We can place the components, we can connect the components, but we can also parameterize the system automatically as well. And that all lends itself to having a very efficient way to build complex models and reduce the amount of time we need to verify the correctness of those systems. So let us now go into MATLAB and we'll take a look at how we can build models programmatically. What we're going to consider is how we build a model of a modular multi-level converter. The base component of a modular multi-level converter is a single cell which has two IGBT switches and a capacitor. This is the model here in SimPower Systems. So we want to use this cell, but we want to automatically build the required number of cells, connect them together, and have them ready for placement into a full power converter. The way we do this is we write a MATLAB script which can build this model automatically. Now I'm not going to dwell on this code. We can make this code available to anyone who emails us and asks for it. Basically what it does is we can ask for a certain number of cells. So I've got 12 cells here, I can actually ask for 24 cells. When I run this, it will automatically build positive arm of that converter with 24 cells, and there it's done. If I look under the mask here and zoom in, you can see there 24 cells. I'll just zoom in a little bit. So each cell is connected in the appropriate way with the correct modulation signal coming in. We'll touch upon the modulation signals in just a moment. But what we have here is the positive arm, which we can duplicate in the full converter, and I'll show you that now. I created a library of different architectures of modular multi-level converters, basically just different numbers of cells, and I'll show you the 48 cell. So we have the 6 blocks. A single block was automatically generated. I can then just cut and paste that positive and negative arms of the converter You could build this whole system automatically as well, but I personally saw diminishing returns there. So I basically just generated the one positive arm and then just duplicated that within the architecture. If we look underneath, 48 cells, I'm sure you can hardly see that on the render. I'll just zoom in a little bit here. 48 cells, exactly the same as you saw before. So I've got different numbers. The other thing you'll notice is we have a PWM generator, which is basically vectorized, and all we need to do is tell it how many cells are in the system, and it will generate the appropriate phase-shifted modulation waves for this. I also have an average modular multi-level converter, which is very useful when we're looking at the system level, and when we're doing some rapid design iteration we may want to do the average value version of a modular multi-level converter. And what that basically means is we use an average value voltage source converter and we feed in pulse width modulation signals which are stacked. So they basically will look like the staircase response you will see from a modular multi-level converter, and those signals are then produced directly into voltages on this model. It means we don't need to model all the physical devices in this version, so it does run faster. We do get faster design iterations, and then once we're ready to do more detailed study, we can bring in full physical architectures. And the other component you see here is a configurable subsystem. This is the block we actually bring into the system level, and we can select any of those models that you see here. If I double click, you can see they're all members of this block. So we can rapidly switch between those. We can either manually select a configuration or we can programmatically select a configuration. So let's now move on to the hybrid electric railcar model. I'll just bring the model up here. So let's just go through the various components. Start at the generator side. So in this particular case, I'm using a standard synchronous machine model. I'm using simplified governor and AVR models. In this case, you can add complexity in here for your own simulations, but I've kept it as simple as I can. I'm really just, got simple controllers to control the speed of the system and the terminal voltage as well. I also have a simple resistive base load in this case. Again, you can put more fidelity in there. You can have a load which is more representative of the actual base load that may be on your rail car. That generator then feeds into a modular multi-level converter. So this is a configurable subsystem. If I right click on this, I can go to block choice and then I have choices available to me. I'm using the average modular multi-level converter in this case. This does not contain the individual models of the switches and the capacitors. It's emulating the effect of the modular multi-level converter by sending the staircase waveforms directly into the average value model. In this case, I'm emulating 48 cells with a 600 Hz carrier frequency. Got a rather simple controller here, nothing too remarkable about this control system. The controller is basically just in place to keep voltage at a constant level and also control the power factor of the system. We then have the DC link, where I've added a storage block. I have not represented a specific technology here. So this goes back to the question of model fidelity. And in this particular case, I just want to assess the operational responses. I want to look at the impact of storage. I want to look at overall storage capacity, charge rate and discharge rate, and determine what values might be appropriate for certain operational scenarios for this hybrid electric rail car. So in that particular case, I don't need to model the technology. I have a controlled current source, which I am controlling from a MATLAB function block. If we take a look here, it's very simplistic for the purpose of this investigation. I'm looking at the current that's being fed to the load. So the current the load is either absorbing or producing. And then I'm monitoring its direction. I'm saying that during a regeneration period, feed the current that's regenerating from the drive into the storage device while honouring the maximum charging capacity of that storage device. And also, if the storage device goes to maximum capacity, stop charging it. So very simplistic, but it allows us to start looking at the impact of certain ratings on this system. I then have the motor drive, which again is another modular multi-level converter. Again, it's an average value model, in this case 96 cells. And we have a permanent magnet synchronous machine as our motor. The controller for the permanent magnet synchronous machine is fairly simple. It's basically a speed control system with an inner current feedback loop, fairly standard. So let's run this. And as it's running, we'll talk a little bit more about model fidelity. So as you're going through what you might call the design cycles, you really want to keep the fidelity of the model as low as you can. So average value models of the converters, just a functional representation of the storage device. But you still need to be sure that you're getting the characteristics in that you need. So having the harmonics represented through the average value converter is definitely an important thing to have. And we also want to be sure that we're modeling scenarios that make sense and getting the information that we need to make engineering decisions on the full system. Once we've been through these design iterations, we can bring in more detail on the simulation. Bring in the full physical simulation of the converters. We can also start looking at specific storage technology. So instead of the functional model, start dropping in proper technology options. So it's done. So let's take a look at the responses here. First thing I'd like to do is just go in and show you the speed response of the motor drive. So we're basically accelerating for 3 seconds, holding speed for half a second, and then decelerating for 3 seconds. Magenta is the reference command, yellow is the achieved, so we're getting a reasonable speed tracking response on this system. We can now look at the voltage being fed into the permanent magnet system. So we see here, we can see the effect of it speeding up. We can also see the impact of the modular multi-level converter. Now we'll look at the source. So voltage is being held fairly constant. As you can see a harmonic contamination on these waveforms. We can look at the harmonics of this. We can double click the power GUI, go to FFT analysis. And what we want to do is select the source voltage. And do 60 Hertz as our fundamental frequency. And let's go up to 40,000 Hertz as our maximum frequency. And do a display. So what we can see here is a total harmonic distortion of 2.01% in this case. And it's sidebanded around the 480th harmonic. This is what we expect. We have a 48 cell converter and our carrier frequency is a factor of 10 above base frequency. So we expect to see the first significant harmonics coming in at the 480th harmonic, which is what we see. So we're confident that we're seeing the harmonic response that we expect. Now let's look at what's going on with the current through the DC system. The magenta response is the current that's being fed to the motor drive. So we can see here that for the first 3 seconds we're going through an acceleration profile, then we drop to constant speed for half a second, and then we decelerate from 3.5 seconds onwards. And so we can see the negative current coming from the regeneration. The light blue response is the current going into the energy storage device. So because the currents went negative, the storage device is now charging up. I've set its maximum charge rate at 20 amps, so we see it charging. And then as the regenerated current drops below 20 amps, we see it tracking. We see the storage device tracking that, so it's still bringing that current into the storage system. And then here, just over 5.5 seconds, we see the storage device is no longer charging. This is because it's reached its maximum capacity. Yellow current, incidentally, is the current that's getting back to the generator. So let's take a look now at the generator response. We'll look at speed, shaft speed. So we can see there during the first 3 seconds, during the acceleration profile, speed increases and then comes down, trying to regulate to 1 per unit. Then we go to constant speed for half a second, and then we begin the deceleration. So you see several kicks in the speed response. The final kick is when the storage device is fully charged. We can look at the generator current. And so we can see here the various stages. Acceleration, constant speed, regeneration, which is significantly reduced because most of the current is going into the storage device. And then we get this kick just after 5.5 seconds where the storage device is fully loaded and that current gets back to the generator. And so this type of information obviously informs the choice of storage capacity, charge discharge rate, and you'd be looking at a number of different operational scenarios as well. In terms of running multiple scenarios, I have a simple MATLAB file here. I'm not going to run it, but I have different speed profiles on the system which I can run through one at a time and simulate the hybrid electric rail system with those speeds and then store the results. This is very simplistic. My intent with this was just to have it for you. If you do want to have this file, take it as your base file and use it to develop multiple test cases or multiple operational procedures for the system. We'd now like to move on to looking at an electrified track, and our first consideration with this is how do we model a moving load. And one way we can do it is to emulate the moving load using lumped parameter segments. What I have here is a little animation. I'm going to run it in just a second. The grey block is the moving load. Blue, green, red and yellow blocks are the lumped parameters in the model, which are going to be driven by appropriate signals to give an overall emulation of movement. So if I just run this, you can see there how the signals are being fed to each of the blocks to give an overall emulation of movement. I'll run this again. Now you're not limited to 4, of course. The more lump parameter segments you have, the more representative your simulation will be of a true moving load. And so you're making that trade-off call between how many segments you need to get the information you're looking for in a particular simulation. So let's take a look at how we put a system like this together. So just like we did with the modular multi-level converters, let's look at the single elements that make up the system. So a single lump parameter segment, if I look under here, I'm basically going to be feeding signals in, and I'm just feeding active power for this particular example. I'll show you how to generate these signals in a minute, but we're basically feeding in these triangular waveforms for each segment. I just have a fairly simple representation of a segment here. Now, this is going to be an AC system. These components can change, of course, depending on the specifics of your system. You may also want to look at DC. That can be done as well. Basically, you're not constrained the type of system you want to look at and what the segment architecture would look like. So what we want to do is use a similar approach to build a line segment. And so we have another script very similar to the modular multi-level converter script. And I can define the number of segments that I want to put together. I'm doing single phase in this particular case. I'm just going to run this and it's going to put together a phasor representation of a system with a single phase line. Of course, you're not limited to single phase. You can make them 2-phase, 3-phase, whatever architecture is needed in certain areas of that system that you're looking at. You can put together your customized components to do this. So we see we've put together 20 of these segments, and we want to emulate a load moving along that line from the source further away. I'm going to generate the signals that we need. This is a visual representation which doesn't in itself make much sense at the moment, so we'll look at this a different way. Let's look at the signals. These are the 20 waveforms which we're feeding into each of the segments. So it's time along the x-axis here, and power, active power up the y-axis. So 200 kilowatt system. The net effect, we can sum these up, and it ramps up and then holds 200 kilowatts constant for the duration of its travel. Back to the model. So this is a phasor simulation, so we're not simulating the full EMT waveforms, although I've set up other examples that will do that as well, that allow you to look at the EMT. You could also put together DC as well, so multiple ways you could do this. Let's just run this. And while it's running, it's going to run for 100 seconds of simulation time, which is the time it takes to traverse the line. In this particular example, I've put in some rather unrealistic values of resistance and inductance in the line segments, just to show visually what's going on with the supply. Yellow is active power, red is reactive power. So as the load's moving along the line, there's more resistance, so it needs more power to feed the constant power load as it moves, which is the ramp we're seeing here. And I've also put in some rather large inductance values, so we can see that the reactive power requirements are changing quite significantly as well during that period. And I'm doing this only for visual purposes. Now if we zoom in, we'll see the impact, we'll see the effect of the way that we're emulating this. You can see, you know, it's like dipping down, and that's a consequence of the triangular waveforms as it's moving along. So if I zoom in, you'll see this. So really the number of segments, as I said before, choose the number of segments that are going to give you the information that you're looking for a given study. Okay, so what we've considered in this webinar is this theme of model fidelity. And by considering two different types of systems, the hybrid electric rail car and also the rail electrification example, you know, we've had a few considerations about the level of modeling detail that we need to achieve a certain objective. When you're looking at putting together complex models, we would certainly recommend that you look at building those models programmatically from base components, and we've shown you examples of how to do that. If you are looking at rail electrification and looking at the impact on grid response of moving loads, then you can emulate the moving load using lump parameter segments. I might also add that you're not confined to a single load using this technique either. You can put in multiple responses, multiple moving load responses to emulate the effect of a different number of loads moving through these segments. And you can clearly move towards much more complex representations of the rail network and the grid system. And we also spoke a little bit about looking at how you can simulate different operational scenarios by using a MATLAB script. Thank you for watching the webinar. If you have any questions, please email me at webinars@mathworks.com. You can also go to our website to take a look at the other recorded webinars that are available. Thank you.